You're enjoying a nice leisurely evening by yourself when suddenly a race of aliens decides to make first contact in your room. Relatable, I know, but stick with me here. As the first of the extraterrestrials descends from their vessel, it accidentally trips on your math homework. Understandably upset, the alien demands to know what all these strange symbols mean. You're not sure what to say. It's been a while since you were in kindergarten. You've known what basic math is for so long that you've forgotten how to start explaining it from the ground up. You go to try and find something to explain with, but the only thing you have in your room is a large number of boxes filled with donuts. Again, relatable, I know. Using the donuts, you're able to easily explain what the number symbols look like. One donut for one, two for two, etc. But it's the symbols between numbers that seem to trip up the alien. And now you're stuck here wondering, how would you explain operations to an alien using donuts and boxes? Chapter 1. Repeated incrementation. So you try to start at what to you is seemingly the easiest mathematical operation. Addition. In one hand you take one donut, and in the other hand you take two. Combining them together makes three. Easy enough, right? But the alien still doesn't have the knowledge to be certain of what exactly addition is. See, the alien now knows only one result of the function, namely 1 and 2 makes 3, and you could show it many more, but since there are an infinite amount of possible number combinations for the input, the alien will always have to guess between infinitely many possible functions to fill the infinite gaps. Alright, so evidently you need to start even simpler with a function that you can clearly describe to the alien with little room for ambiguity. But isn't addition the very first thing you learned in school when it comes to math? What could be simpler than that? Then it hits you. The very first thing you learned in school wasn't addition, it was counting. Incrementation, of course. Besides the identity function, perhaps the easiest one to fully grasp. It only takes one whole number variable as input and returns the smallest greater whole number, or in layman's terms, the number after it. You manage to explain this basic concept to the alien, and as far as the two of you can tell, it gets it now. From this point, how do you explain addition? Let's look at an example. 5 plus 4. You already know the answer's 9, but for the alien to understand why, we first need to truly understand what's going on here. Let's start at the bit we know the alien does understand. We have 5. Now, it's tempting to say we have 4 as well and add these quantities, but our extraterrestrial friend doesn't understand the idea of add. What to humans might seem intuitive could seem wholly different to it. What the alien does understand, though, is incrementing, and then it clicks. You start with 5, the first number, and then increment 4 times, since the second number is 4. You generalize the definition. A plus B means starting with A, then incrementing B times. And suddenly, the alien gets it. You've succeeded at explaining addition, but the alien insists you explain the other symbols as well. So next up, multiplication. You start explaining how you learn it in school again. You take 2 boxes, each with 3 donuts. How many donuts in total? 6. But the alien again doesn't seem to understand that you're looking for the total number of donuts, or at the very least they can't be sure. Time to go back to the drawing board. Again, your alien understands starting with 5, but how to explain times 4? Well, let's get a little more abstract. If we look at this as plus 5 times 4, we can see a repetition again. If you repeat plus 5 4 times, you get a sum resulting in 20, which naturally is the correct answer. Your boxes of donuts are, at least to the alien, repeated additions, which in turn are really just repeated incrementations. You generalize as such, and the alien once again seems to get it. Now you've grown curious. Will the same method work for exponents? You write down your example 3 to the power of 3. You could try explaining this in a way that makes intuitive sense to humans, but the alien already looks bored as you reach for your donuts. Well, let's try the method that's been working so far, right? 3 to the power of 3 is really times 3 repeated thrice. And yeah, that seems to work out pretty well. The alien watches as you generalize this rule. It seems to understand exponents now too. It looks again at your homework and grabs a random problem to do a sanity check on its newly acquired knowledge. Alright, 2 to the power of 3, simple enough. The alien uses the method you've just started to bring the problem back to a form it understands. Times 2 times 2 times 2. Now it does the same again. Times 2 is really just plus 2 plus 2. And plus 2, that's really just incrementing twice. In reality, you've just repeated incrementation twice, twice, thrice. The alien works out the math and arrives at the correct answer, 8. It has mastered addition, multiplication, and exponentiation. Chapter 2. Operations inverted. Just as you think you're done explaining basic arithmetic, the alien flips over your paper to show the other side of your homework. It demands to know what these symbols mean as well. The minus sign, division sign, and square root symbol present themselves proudly on your homework. Looks like you're not quite done here after all. Thinking it over, you eat a donut, leaving one less in the box than before, and an idea strikes you on how to explain subtraction. We're going to use the concept of decrementing. Decrementing is essentially the opposite of incrementing. Instead of going up 1 in the list of whole numbers like with incrementation, you go down 1 when you decrement. It is the inverse operation of incrementing, meaning that A incremented equals to B is logically equivalent to B decremented equals to A. Subtracting, then, is repeated decrements. Much like addition in a way, A minus B means starting at A, then decrementing B times. The alien thinks about this for a bit and then comes up with the following sanity check. Addition and subtraction, it proposes, are also inverses of one another. X plus n equals y, and y minus n equals x. You agree. In fact, you add, the same would be true for y minus x equals n. Here, let's make a quick table to see where we're at. We take the following empty table where each cell corresponds to a certain function over the variables a, b, and c. Every column corresponds to one of the variables, which will be the unknown variable in this column. So here, if we know a is 1 less than b and we have a, we increment to find out what b is using incrementation. However, if we know b and not a, we decrement from b to find a. As you can see, this forms a row of inverse operations. Next, we can add our tower of iterative operations over incrementation above it. We start with addition, which is repeated incrementation, then multiplication, which is repeated addition, and finally exponentiation, which is just repeated multiplication. We use these arrows to signify that an operation is derived from the one below it by iterating, in this case, c times over a. Now we add our final element of the puzzle, the inverse of addition, which we've just seen as subtraction. And conveniently, it's also what happens when you repeat decrementation from b an equal number of times. Now, we want to fill out these missing squares. By the table, they look to be the inverse operations of multiplication. However, there's also a pattern going on where every cell appears to be what happens when we repeatedly perform the operation below it. Therefore, it looks like we can derive these cells by either finding a function that iteratively subtracts, or we could simply find the inverse of multiplication. You decide to take the second course of action. You take another look at multiplication, which you now know is another way of saying addition repeated a certain number of times. You take the number of boxes, 2, and then take the amount of donuts per box, 3, and then you know the amount of donuts between the two boxes would be 2 times 3 equals 6. To convert this function, we need to change the unknown from amount of donuts to, for example, amount of boxes. Say we need 6 total donuts for a party. We know that each box contains 3 donuts. So how many boxes do we need? Well, 6 divided by 3 equals 2, so we need 2 boxes. This means that one of the inverses of multiplication is division. Now we hide not the total amount of donuts or the total amount of boxes, but the number of donuts per box. Say you've bought 2 boxes, each with an identical but unknown amount of donuts. Your friend then comes in, takes a peek in both boxes, and tells you that the total number of donuts among them is equal to 6. You can then conclude that because 6 divided by 2 equals 3, there must therefore also be 3 donuts in each box. The other inverse of multiplication therefore is also 3. The alien doesn't look interested in your donut explanations, so maybe it would be more productive to simply show the table again. Generalizing this to fit our table, we can now see that both the inverse operations of multiplication are division. Looks like the table is almost done. You need to find the inverses of exponentiation and you'll be done. However, the alien seems to have other plans. It scribbles down 2 arrows, seemingly asking you to test your earlier hypothesis that the cells above subtraction actually employ repeated subtraction. You think it over for a second. So you have some mystery operation which performs minus a b times. Well, this kind of looks eerily similar to earlier when multiplication was derived from addition, no? In fact, it looks identical but using minus a instead of plus a. So if plus a iterated upon yields multiplication, then minus a iterated upon yields negative multiplication? Yes, in fact it does. By first multiplying a by b, then subtracting that product, we get the operation we were looking for. It turns out that repeating an inverse operation like this simply gives you an iterative version of its inverse. This property even holds for division as well. Dividing b times by a can be done by taking a to the power of b, then dividing by it. Anyways, those operations aren't unique as they can be made up of the ones in our table right here. We don't need to consider them too much. The alien understands and allows you to move on to the final 2 cells. Since we've already established that finding the iterative operation of division doesn't yield what we're looking for, we instead need to find the inverted operations for exponentiation. Both addition and multiplication are seen as commutative operations. This means that their inverses are both the same because having a or b be the unknown variable is identical. Exponentiation, however, is not commutative. Therefore, it has 2 different inversions. Let's find both of them. Just for us humans, let's quickly recap exponentiation with donuts. If we have boxes that each contain 2 items as such, and they go 3 layers deep like this, then the total number of donuts ends up being 8. Now, if there's a curtain blocking the view, like this, but you know there's 3 layers, and a friend peeking behind the curtain tells you there's a total of 8 donuts, then you can use the cube root of 8, or the third root of 8, to find the amount of items per box, being 2. For the other inverse, let's say we know every box has 2 boxes in it, and we're looking for the depth where there are 8 boxes. Using log base 2 of 8, we find that this is at depth 3. And with that, your table is done. You've explained all the most common mathematical operations. The alien is enlightened and ready to leave, but now that you're already busy, might as well get into some of the interesting stuff, right? Chapter 3. Beyond the Basics. Now you're out of operations and out of donuts, but the alien is still in your room and its hunger for mathematical knowledge has not yet been satiated. Sure, the table has been filled in, but we can go further. Why stop here? It's going to continue by itself to research some more fun interactions of these operations. The alien looks over at your table and looks at the possible routes to continue on from here. Looking at that column on the left, it decides to try and create an operation that iterates upon exponentiation, continuing the tower upwards. We'll call this operation tetration and make the symbol a double up arrow like this. So let's look at 3 tetrated to 3. Intuitively, this would look like this, 3 to the power of itself 3 times. So we're done, right? That's it. Well, not quite. Since exponentiation is non-commutative, the way we interpret this operation will actually yield different results, as you can see here. We take the second pair of 3 first, we get a far larger resulting value than if we take the first pair first. It is generally agreed upon that we take the first definition, where we work right to left. This one is tetration. But let's take a look at the other operation first. Let's look at a table of this so-called left-leaning tetration. You might notice that each row is equal to the previous one to the power of a, except for the first. This is actually always the case. Therefore, formally, we can define the operation like this. Now, this looks quite familiar. In fact, one very mathematically inclined individual could say it kind of looks like the equation in blue here. And in fact, they are indeed equivalent. I am not going to bore you with the whole proof, but feel free to pause and read along if that's your thing. It's a simple proof by induction. Alright, so that version of the definition isn't really giving us anything exciting. What about the other definition though? If we assume our titration goes right to left, we do in fact come up with an iterative form of exponentiation that is quite unique. And there it is in our table. You might notice we've also added the inverses of this operation, the super square root and super logarithm. Maybe you're wondering if we can go up even higher, and the answer, luckily for you, is we can. Iterating upon titration gives us penetration, which has its associated inverses too. And after that, you can even iterate on pentation. Iterate and iterate and iterate ad infinitum. However, this isn't really that useful, since the values you get are quite large, quite fast, even if just for titration. To illustrate this, here you can see some of the incredibly high values you get on even the lowest titrations, and it goes without saying that pentations get larger even faster. This also has as a consequence that since titration and its successors only take integer values from our definition, there's very few actual roots and superlogarithms that yield an answer, with integers that is. These reasons are a part of why these operations are typically not taught in school. There are approximations of titration and pentation and so on that fill in the gaps, but this video isn't about those, so we'll move on. Because our alien friend has just had another interesting thought. We think back to our operation from the leftmost column, addition, multiplication, etc. Now, what happens if we plug two 2's into these operations? As it turns out, the answer always seems to end up being 4, but does this pattern hold forever? Let's denote a function like this, where f1 is addition, f2 is multiplication, and so forth. We then assume an arbitrary fn 2, 2 equals 4. If we can now prove that fn plus 1, or the iterative function of that function, also equals 4, we can use an induction to sort of domino effect backwards to proving this holds for all operations. So let's prove it then. Quite simply spoken, fn plus 1 if the function fn repeated 2 times on 2. Since we've assumed this equals 4, we're actually already done. Short and simple proof, albeit a bit informal, but yeah. It turns out that any function of this kind, with 2 and 2 as its input, will yield 4. Regardless, it looks like we're done here. All these operations are... Okay, actually, while they were a helpful tool for explaining, incrementing and decrementing don't make much sense for non-integers, and they aren't even binary operations like all the others, so yeah. Now we have a nice and succinct table of all the operations you know and love. There's addition and its inverse subtraction, its iterative operation, multiplication, and its inverse division, and finally the further iterated exponentiation and its inverses, the root and logarithm. The alien passes your homework back to you, clearly grateful for the knowledge you've bestowed upon it, and with that it leaves our galaxy, hopefully to never return to ask questions about math again. And that's all, folks. I hope you've enjoyed this little math video. It's not breaking any new ground by far, but I've always found this an interesting topic, and I wanted to share my take on the math video with a black background and minimal animation genre. Anyways, don't forget to view this video more than once, then iteratively view it once more n times, then iteratively do that n more times, and then iteratively